Hello and welcome to this video in which I'm going to explain to you how linear regression works. Let's get started. Well, first of all, I'm going to put linear regression into its context. That is, to the family to which it belongs. So, linear regression belongs to the large family of general linear models, or GLM in short. There are certain assumptions to the GLM, namely that the residuals are normally distributed, and this is something that we will get to later on. Under the general linear model, we have the analysis of variance, among which the ANOVA, ANGOVA, etc. These are topics that will be covered in another video. We're going to look to the regression analysis. Under it, we have the so-called univariate and multivariate analysis. Univariate means that we only have one independent variable. Multivariate means we have multiple independent variables. Under both we have the so-called simple and multiple regressions. Simple meaning we have only one dependent variable, and multiple meaning we can have multiple dependent variables as well. In this video I'm going to explain to you how simple univariate linear regression works. The reason for that is if you understand this most simple form of linear regression, you know basically how all linear regression types work. I'm also going to explain to you a little bit about the multiple linear regressions, and just to show you what possibilities there might be. In essence, what we're after with linear regression is we want to find the relationship, or more specific, we want to describe the relationship between two variables, A and B. Within regression analysis, we're not talking about causal relationships. We're only talking about a relationship, which might be causal or not, but we cannot state that based on our regression analysis. However, typically, we are looking to the variables like x and y, in which y is the dependent variable and x as the independent variable. But remember, despite the fact that we typically speak about dependent and independent variables, we cannot imply causation. Okay, let's go into simple linear regression. So we have our x variable on horizontal axis, that's our independent variable. And we've got our dependent variable y on the y-axis. So if we have some measurements, like these red dots, we're tempted to, well, look for the relationship, and in our minds we draw a line through them. And we can see that this line fits nearly perfect on the 4 data points. But typically that's not what we get. Typically we have a little bit more variation in our data. Like these blue dots. These blue data points show some more variation, and the red line might be a good fit to them. It runs kind of right through them, but we don't know for sure. The line might be a bit less steep than the red model, or steeper, or we don't know. That is why we need linear regression or the calculations to find out what is the best match for these data points. We can also have data points more scattered, like the green dots. It is hard to see any form of relationship. And it is rather likely that we will find a relationship, actually we will find no relationship, like a more horizontal one, which means that whatever value I take for x, my y value does not change. In this case, there's no relationship between x and y. So, in essence, linear regression determines the best fitting line to the data. This is our regression model. It also determines how much variation in the data can be accounted for with our linear model, and it determines the mathematical equation of the linear model. Having the mathematical equation, it will help us in actually making predictions. For example, if we want to make a prediction on this for this x value, we have no data point. But if we have the equation for the red line, we can calculate the predicted value of y given this value of x. So for example, let's look at some data points in which we're putting the costs for advertisements next to the profit a company might gain. On the x-axis we put our independent variable, and on the y-axis we put our dependent variable, or the variables that we assume to be dependent. In this case we assume profit to be dependent on the costs that we spend on advertisements. Now what we see here is this is one data point. It belongs to a value of 10,000 euros for advert costs, and there we find a profit of 20,000. So you see this line in my table represents one data point. This line in my table, 12,000 on advert costs on advertisements, we find a profit of 23,000. So that's also one data point. And so we see for every row that we have in our table, we find a data point. Seeing these data points, again, we are tempted, and that's actually what we're looking for, we are tempted to draw a line through them, to find a relationship between these variables. Now, we can draw a line there, but now the questions are, what is the mathematical equation of this line, and how good does this line fit to my data? Well, these two aspects are covered in the following slides. The standard formula for a straight line is y is a plus b times x. X being the independent variable, y being the dependent variable. And what we see is with a straight line, we have a certain intercept. So if x is 0, there is a certain value of y. This is called the intercept, or in this formula denoted as a. Because if x is 0, this term is gone, and we are stuck with only a. Now, b is the derivative of our line. So if I make one step on the x-axis, how much is my y value going to increase? So the steepness of this curve is represented by b. Now, if we're going to use this straight line, we're actually simplifying reality. Because in reality, things are never that simple. It's not like we can predict relationships by just one straight line. There are other things to it that we might take into account, and also a lot of factors that we cannot take into account. If we're going to simplify reality by just a linear equation, we will see that there is something next to that we did not take into account. This is called our error term, and if you look to the figure to the right, we see that our model, the red line, does not capture the blue data, not all of it. There are some errors over there, so whatever we did not take into account, that's the epsilon. So we are simplifying reality. Now, we want to make just one equation for one line, and if this is reality, y, then what we're after is y hat. Y hat is the predicted value of y given x. So by denoting or showing that hat on top of y, we know that we're now talking about a prediction. What we actually assume is, with this prediction, we assume that the error term averages out. Well, actually there are two assumptions to it. First of all, that the error, or whatever we did not take into account, like these errors here, overall they are normally distributed. These are these residuals that should be normally distributed, and if they're normally distributed, they will average out. Meaning that this error term is not longer incorporated in our formula. It has an effect on other calculations, like how good our line fits on our data, etc. But regarding the formula itself for the straight line, we do not take it into account anymore. So let me explain to you how we find the best fitting line. I'm going to show you one method to do so, using the minimum squared error method. There are other ways to calculate the best fitting line as well, but minimum squared error gives you an idea of how this is done. The best fitting line can be found if we minimize the total error, or the difference that is between our model, which is the line, and the data points. So in this figure, it is shown by the blue bars, and these blue bars represent the difference between data points and the regression model. And this is all captured within this formula. So what we see here is that the predicted value of y giving measurement I and the actual value of the data point at position I, subtract them from each other so we find the difference. So that is what's happening here. So this is measurement 1. We've got y value 1, and over here we have our predicted value number 1. This difference is what we find in this formula. These little y's over here, these represent our data points. So y is 1, I is 2, I is 3, I is 4, etc. If we sum up these differences, we will find the total error. Now there's one more thing to it, that's the square over here. If we would not square these differences, what we would encounter is that they tend to cancel out, because sometimes we have a positive difference and sometimes we have a negative difference. Adding them up, we will end up around 0 again. So if we square things, the negative values become positive as well. Adding up all positive values gives us a measure of the difference between the actual data points and the predicted values of y. If we minimize this equation, so finding the lowest value, we know that we found the best fitting line, because overall the error is smallest. Now, we can do these calculations by hand. I'm going to show you how to do this, just to show you in essence how it works and what it is that we are doing. Normally you would use a software package to do this for you, because it will save a lot of time. For this example, I take our measurements from the advert costs and profit example, but only the first 4 I choose to represent like 10,000 euros, just to make the numbers a little bit smaller. Okay. So this is the formula we're after. Y hat is a plus b times x. We want to have the value for a and we want to have the value for b. This is the formula for finding b. This is the formula for finding a. If you want to find a, you have to know b, so we start with b. Now, in this equation, which might look challenging at the first time, when looking to it a little bit more closely, we see that it's not that challenging at all, actually. Because there are elements in it that are very easy to calculate. So first of all, the average of x, the average of y, and we subtract it from our x and y values. So we can do that. Here we have x minus x average. So we have the values of x, 10 plus 12, 14, 16. Adding them up gives us 52. Dividing it by 4 gives us our average, which is 13. 10 minus 13 gives us minus 3. 12 minus 13 gives us minus 1. 14 minus 13 gives us 1. 16 minus 13 gives us 3. Okay, we can do the same for y. Adding all these values up, 20 plus 23 plus 27 plus 30 gives us 100. 100 divided by 4 gives us 25. 25 is the average of y. And again, 20 minus 25 gives us minus 5, etc. Okay, now what we need to find is not just the x minus x average and y minus y average, but we need to multiply them. That's on top of this equation. So we can do so. So minus 3 times minus 5 gives us 15. minus 1 times minus 2 gives us 2, etc. By doing all this and summing them up, we get the value of 34. So we see that on top of our division we see 34, just one number. Okay, now the bottom part, we again see x minus x average squared. So the x minus x average, we already found it, it's over here. Now we only have to square it. So minus 3 squared gives us 9. Minus 1 squared gives us 1, etc. Now by doing that for all four measures and adding them up, we get the value of 20, which we should put here, 20. So B in the end is a simple division of 34 divided by 20, giving us the value of 1.7. Now that we have B, we can calculate A, because A is simply the average of Y, which we calculated to be 25, minus B, 1.7, times X average, which we calculated to be 13, giving us a value of 2.9. So in the end, our formula will be Y hat is 2.9 plus 1.7 times X. Now we have the formula for our equation. I want to get to something we call, well, it's a measure of goodness of fit, and it's called the R squared. But before we can get to the R squared, I have to tell you about the R, which is our correlation coefficient. It indicates actually how good our relation is between two variables, and it also shows us the direction of that relation. So R can be any value between minus 1 and plus 1. If we find an R of 1, we know that we have a positive relation or positive correlation, meaning that if X increases, Y goes up. This is a positive correlation. A negative correlation, if X goes up, Y goes down. And if we have no correlation, R is 0, we see that there's just a massive cloud of data points and we cannot really see that there's any relation whatsoever. You see, on average, that is. Now, an R value, the closer it is to either 1 or minus 1, the stronger the relationship is, or we could say the stronger the correlation is. Now, if we get towards 0, we see that there's no correlation. So we have, with the R, we have a measure that shows us the strength of the relationship. So closer to 1 or minus 1, it's stronger, and the direction, so positive or negative. Here on the bottom we see the formula, and it kind of works the same as with calculating the A and the B values in our equation of Y hat. If you continue doing so, we calculated this value of 34. So this is the sum of all X minus X average squared times Y minus Y average squared. If we take that from the table in the previous slide, we see that we will end up with a correlation coefficient of 0.998, which is an almost perfect positive linear relation between advert costs and profit. Now, in reality, if you find a correlation that is that nearly perfect, there should be some alarm bells ringing, because it's almost too good to be true. It can happen, but it gives you a reason to look into your data again. Now, from the R, from our correlation coefficient, we get to the R squared. And this R squared is a measure of the goodness of fit of our regression model, of our line. How well does it fit to our data? So in essence, the R squared value, which is a value between 0 and 1, represents the percentage of variance in our dependent measure that our independent measure explains according to our regression model. So to make this more visually, if we see that, for example, here to the right, we have our data points fairly close to our regression line. In this case, we have R squared close to 1, because our regression line fits the data pretty well. If, however, on the left side, our data is very scattered, we can see that I say that our square is about 0, which actually means that, of course, we or our computers can calculate the best fitting line. However, the difference between the best fitting line, so of course our computers can calculate the best fitting line, so with the lowest residual error, but having a line a little bit different, for example like this, a little bit less steep, or maybe like this, yes, the overall residual error might be bigger than with the black line over here, but the difference is not so big. So it means that we are rather unsure whether we should actually take the black line or one of the red lines, giving us low confidentiality of the fit of our model. Another way to look at it is kind of to say that we have a certain region of confidence, so a kind of confidence interval around our regression model, and a certain percentage of our data points fall within these boundaries. So kind of the variation in our model, the variation in our data, some of it falls within this interval and some outside. The more that are falling outside of our interval, then they're not explained by our model. This is just a metaphor, not necessarily true, but it helps us trying to let you understand what is going on. In essence, it's not true what I'm saying, but it helps you understand what this R square value is representing. So in our case, the R we had was 0.998. If we square it, we get to an R square value of 0.996, which again is fairly high. So what we found was that the relationship between the investment that we did in advert cost and the profits had a correlation coefficient of 0.998. We found a mathematical equation of y hat is 2.9 plus 1.7 times x, and an R squared value of 0.996, or in other words, that 99.6% of our data was explained by our model. So I talked about simple linear regression, and now I want to talk about that there are other types of linear regression as well, not multiple linear regression. So with simple linear regression, we just had one predictor, x, and we had a beta weight to it. So if we would write it down in a more general form, we would have an x1, predictor number 1, and the weight that is and the weight that belongs to x1. Now, in the case of multiple linear regression, we have still our intercept. We have predictor number 1, predictor number 2, 3, etc. And we have specific weights, so these b's, or in this case now called betas, to the predictors as well. The higher the beta, the stronger a predictor actually influences our model. Now, next to having only one or multiple predictors, we can also think about the type of relationship between them. So it can be linear with just a straight line like we had in this formula, or any other type of equation. So for example, over here, one other type would be a second degree polynomial function. And what we see is that the line fits our data better. We have a higher R square value even, instead of 0.96, 0.99. So there's a better fit. The question that we have to ask ourselves is, okay, we find a higher R square value, which is generally true when we use a higher order polynomial function. But you can ask yourself whether this higher order, or let's say more in general, the more complex equations to find a relationship between the two variables, is it always better? This is not always the case, but this is something that's beyond the scope of this video. Now, a polynomial function is still linear. There are also other types of functions like quadratic or sigmoid, etc. So just so you know, there are all kinds of lines, let's say, that you can fit to your data, and you have to find the best fitting model to your data, which might be linear, but might be another type of equation as well. Okay, now we calculated the R squared, we calculated the values for a linear equation, and now the question is, can we conclude that the linear model that we made actually fits our data, yes or no? We can do so by using statistics. And actually what we're after, so we're doing a statistical test, and what we're testing is whether the model we found fits better to our data than no relation whatsoever. So no relation, it's the Aether-A, it's the null hypothesis, meaning that my predicted y is equal to y average. So if we would put that in a graph, that if we have data points, for example, they're looking like this, we say that this would be y average on the average value of all the y's, and the null hypothesis states that y average is equal to our prediction. And what we want to find out is whether our prediction, whether it's actually different, so not equal to y average, and with what certainty we can state that. So that's what we're going to find out now. We're going to determine the level of significance of our regression model. To start, we have to find the sum of squares of the residuals and of the regression. So we've got two formulas here. You see that we're repeating certain steps, right? So again, you see y hat, y average, y hat, and this is the actual y value. So for the sum of squares for the residuals, we see these are the blue bars found over here. What we want to find out is what is the difference between them, so data points and model, and how big is this value. So we can do the calculations, and we find that it is 8.54 times 10 to the power of 6, so a big number. As its regression, we calculate as our predicted value minus y average. Y average, as we said, that this is our null hypothesis, right? So how far do we deviate from our null hypothesis? That's actually what we're figuring out here. And we found that it's 2.23 times 10 to the power of 8 in the end. Again, a massive number. Now, we're going to use the so-called F statistic here. It's from the analysis of variance. And to find that, what we do is we have the sum of squares of the regression divided by this term, and all that divided by the sum of squares of the residuals divided by this term over here. Now, this term is called df1 and df2, so df stands for degrees of freedom, because both the aspects have a separate degrees of freedom. G stands for the number of betas in our regression model. We have 2 in this case, because we had y hat is beta 0 plus beta 1 times x1, right? The more general way of writing things down. So we've got 2 betas, minus 1. And we have the SS residuals divided by a capital N, which is the total number of measurements, again, minus the number of betas. If we calculate this, we get to the value of 130.57. So this is the F value that we find, and we have to compare that with something called the critical F value to find out whether we can speak of a significant difference. Now this critical F value, we can find that using a table. This is a printout of a table, so this df1 was 2 betas minus 1, so it's 1. df2 was total number of measurements, minus our 2 betas gives us 5. Now, when looking this up, we see that df1 is 1, so we have to look in this column. df2 is 5, so we have to look in this row, and we end up with this value. So, in the end, our F critical is 16.258. Now, the question that we need to ask ourselves is F that we found, the F value that we found, bigger than the critical F value? And if that's the case, we can say that our model is significantly better than having no model, the null hypothesis. Well, in this case, that's true. So, therefore, we can state that the linear regression that we found fits significantly on our data, better than having no relationship whatsoever. We can do these calculations by hand, and I showed you just to show you that what is it that we're comparing against. But typically you will use something like SPSS as a software package. This is the output of SPSS, and it shows us again the F value. It shows us the R squared value. It also shows us the coefficients of the formula. So let me walk you through it. So first of all, the F value. You see that it deviates a little bit from what we calculated, and that's because in our calculations we did round up numbers, etc. And SPSS calculates the F value with a little bit more precision. So that's why it can deviate a little bit from what you calculated by hand. It also shows us the R square value. Same is true here. SPSS works a little bit more accurate than we did by hand. Also, we only incorporated a portion of the data points. SPSS included all. So now we get an R square value of 0.963. Now the values over here, these are coefficients, meaning y hat is beta 0 plus beta 1 times x1. Beta 0 is our constant. Plus 1.411 times x1. So this is the formula that we get in the end. Now, we also want to find out whether our model is significantly better than having no relationship no relation between variables whatsoever. And we know that it was significant, right? Because 130 is bigger than this 16 point something of the critical F value. SPSS actually calculates this level of significance, and it shows us that it is very, very low. Most important for us is that we want to know that it's lower than 0.05, which is typically the alpha that we choose. Here we find significant levels as well, which are very interesting actually to look at, because we can actually find out whether one of our variables, or sorry, one of our predictors actually contributes significantly to our model. And we can see here that both the beta 1 and the beta 0 contribute significantly to our model. If you have a multiple linear model, there will be another variable here as well. Let's say variable 2 with some values. And it again will give us a significance value, and let's say that it's 0.1, for example. In that case, we know that this is higher than our alpha, right? 0.1 is bigger than 0.05, meaning that this second predictor actually does not contribute significantly to our model. So I go through this rather fast. In another video I will explain in more detail how to get to these numbers and how to interpret them. But for now I want to thank you for your attention and leave your comments below.